welcome back to session 2. Let's start it here. So what we're going to talk about here is the realities of construction. And we have two great speakers and also myself to talk to the structural engineer's influence on project sustainability from the construction and from the deconstruction perspective. We'll have time for questions and answers at the end, so please submit your questions in anticipation of that. So I'll get us started. First out of the three of us, I'm Schlaich, Bergermann Partners Sustainability Lead and an engineer in their New York City office. I'm also a visiting scholar with a circular construction lab at Cornell University. And much of my design and research work focuses on overcoming the technical and practical challenges that are found when the circular economy and structural element reuse executed on real projects. So in kicking us off, I want to share some work that SPP have been involved in over the last 4 years at the Montreal Olympic Stadium. The stadium's always been a beautiful structure, but today it's also an exciting circular economy opportunity. I'll briefly speak about the project history, the goals for reusing the roof, and then I'll explain our circular economy approach and I think crucially some of the lessons learned so far from the project. The actual sport of the Montreal Olympic Games in 1976 is remembered as a success, and the history of the stadium itself is a little bit more complicated. In advance of the Games, the stadium construction was impacted by corruption and strikes, and this led to the envisaged roof and supporting tower not being finished in time for the Games. Despite this context, the construction of the stadium proceeded rapidly and impressively when it was in motion, and the Quebec engineers and workers assembled the stadium in less than 18 months. A decade later, the tower construction was completed and an innovative retractable roof was installed. This roof was supported by the tower and could be furled and withdrawn up into the tower, a bit like a squid. But due to damage and deterioration, this retractable roof was replaced with a static roof, only a decade later. This replacement roof has now come to the end of its service life and is being replaced as we speak with a new static roof. This new roof incorporates a ring of glazing at the perimeter to let natural light into the bowl, something which the other roofs didn't have. The roof replacement, it presented an opportunity. In 2021, SPP, we began discussing this with the Parc Olympique, the organization who are leading the renovation. And what we wanted to talk about was what could we do with the structural materials, the steel, the cables, and the architectural membranes that were being removed as part of the replacement process. So instead of a linear economy approach, demolishing the roof and recycling the steel and landfilling the membrane, together we proposed the potential for a circular economy approach, where the roof deconstruction took place instead of demolition, and we reused those materials. There were two key motivations for this: cultural heritage and an environmental aspect. Element reuse could maximize continuity for the community and the stadium's heritage. In a similar way to sort of the historic masonry element reuse that can be seen in Rome, where the picture on the left is the Arch of Constantine, and it tied different eras of control into display and public work. So there's some appeal in maintaining aspects of the old stadium roof and keeping them visible for the community. There's also a really clear environmental benefit to reuse. So this in-press study by Juliana Berglund-Brown at MIT quantifies the embodied carbon benefits of steel reuse as opposed to recycling. With the potential for reused steel to have 25% of the embodied carbon emissions of recycled steel. Deconstruction and reuse is also something that's been done before, with successful recent examples in North America, including the Boulder Community Hospital deconstruction and reuse project that KLNA led in Colorado, as well as an expanding industry of steel reuse in the UK and Europe. So these previous case studies have outlined a roadmap for how this can be done, particularly this document on the right from the Steel Construction Institute in the UK. On the Montreal roof project, what we really were looking at is, could we resolve some of the questions which were related to steel reuse and deconstruction in the Canadian market? So could we successfully deconstruct and use elements for a non-standard and structure with quite large pieces? And could we do this in an economically more geographically spread area, Quebec and Canada, as opposed to relatively compact countries like the UK and Switzerland. So first, we needed to clarify what was available for reuse as part of this project. Not the whole stadium is being taken down, only that roof and the cables supporting it. And we then went through archive drawings and reports to understand the details, element types, element materials, and quantities to produce an inventory which clarified all the subgroups of steel sections, steel cables, and architectural membranes that were available. The potential element supply of the project. These varied from 1¼ inch to 5-inch diameter steel spiral strand, steel pipe struts which are 20 to 60 feet long, and between 1 foot and 3 foot in diameter. Our project approach was involved starting with this potential supply of elements for reuse, and thinking about what the potential demand would be at the end for reusing these elements. So we have supply on the left and demand on the right. Throughout the continued development of the project, what we're looking at is how the realities of a live construction site would narrow down that supply, and how the feasibility and economics of actual projects and demand would reduce what we could do with that material. So kind of like a sports bracket, we'd end up with a few projects which would connect that supply and demand together. The first thing we did to generate demand for how we could reuse these elements from the roof was to look at an internal design competition. So at SBP, we invited all 200 staff across the 8 international offices to submit ideas for structural interventions using the potential element supply from that inventory. A second method involved local architects, engineers, and developers in Montreal attending a workshop to discuss whether these elements would be directly suitable for replacement on projects that they were working on already. And a third method was an international design competition that was launched by the Parc Olympique, which is awarding prizes for ideas that reused the potential element supply from the roof itself. So conceptually, this created 2 ends. We have our potential supply on the left, and we have over 50 potential projects which could use this material on the right. These 50 projects were narrowed down further. The first step was looking at the internal schlaich Bergermann partner in projects and selecting 4 of those for development into concept designs. So we used internal project hours to get for 4 of these selected projects a calculated structural system and a bill of quantities that we could use to then develop some estimates from. From all the entries to the international design competition, 9 were selected by an interdisciplinary panel of judges, and together with the ongoing review of the expressions of interest from the local AEC community, this left a narrowed project demands selection. So only a few projects from that 50 were taken forward to the next step. Once we had this narrowed down project approach, we looked at reducing the potential supply further. So we assessed the type of structures that we needed and the types of elements that were needed in the structural design, and narrowed down the materials that we would want to salvage from the deconstruction process for these specific projects, and also looked at which elements would be potentially useful for the commercial reuse industry in the area. So steel pipes for micropiles, or reusing steel cables for rural suspension bridges. So together, this gave us sort of a refined element supply list, where for materials we'd look for saving between 20% to 100% of a different element type. While for others we might say, well, the architectural membrane is maybe more suitable for making products like bags, or some of the elements were maybe such unusual shapes that they would be more suitable for recycling. This targeted set formed a wish list for what we would then begin to conversations with the contractor about what could be saved on site. The first challenge on site was related to moving elements. So we had our wish list, but some of the elements had really large cross sections, and that meant that there was a risk of overloading the planned on-site craneage. Instead of lifting out 45-foot pieces, some of these would need to be cut down to size to say 15-foot lengths. So this would obviously reduce some of the potential reusability of elements that we're dealing with. Another aspect was understanding the typical cable removal process and lifting sequence. So to ensure the condition of the cables was well maintained, we would look to reduce the radius that the cables were curved around. But the initial plans lifting and removal of cables on site led to some undesirable cable kinks over tighter radii than we would have wanted. So both of these presented opportunities to talk about lifting challenges as part of a deconstruction process, really much earlier in a project. Deconstruction processes also vary to demolition, and in salvaging the cables, we needed to look a little bit at additional care and training to ensure the condition was maintained. So when cutting cables, the strand should be secured to stop unraveling, and often that can be done by tightly wrapping a wire around the end. In some situations, there were available aluminum clamps that we could reuse from other parts of the project, but in other situations, the fixing wasn't done properly, and we were losing some material due to fraying. I think earlier conversations about different preparation processes for deconstruction compared to reuse would have been valuable here. Much of the roof that was being taken down and considered for reuse was installed in the 90s, and therefore the steel coatings were free of lead. However, some of the elements were installed in the 80s and still had leaded paint, and this always, I feel like this comes up on every project. It always highlights the importance of a really detailed survey on site in advance to make sure we know what's there and what we're dealing with. The contaminated lead elements were excluded from the reuse aspect as part of the contractor agreement. So always visit your site and make sure you know what's there, even if you think you know what's there. In general, the painted coatings that were there were in good condition, and the material was well maintained. But some of the coatings were damaged, and in general, all of the steel was going to need to be stripped and recoated to get up to a position that it could be reused again in the future. And I think this is actually an assumption which we should really always consider for reuse of steel elements is a complete stripping and repainting of these items. Once the elements were deconstructed, they needed to be stored, and while there was some space on site around the stadium in loading areas, there wasn't enough space for everything, and this meant that some potentially really valuable elements, which were particularly large, couldn't be stored and had to be sent for recycling due to logistics challenges in the construction site. Later on, additional storage was found to send materials to, but that wasn't available then, and getting that lined up is, I think, really important. The final challenge in element reuse was the length of the elements. So these longer stay cables with large diameters needed to be ideally wrapped, re-spooled on drums so that we could get the maximum use out of them. But because of the ability of the currently available equipment that they had, these cables are instead cut to 50-foot length for removal on trucks, and this obviously really limits the reuse of some of these larger pieces. So with all these lessons incorporated, we had a slightly different final available element supply compared to our targeted one, and this is what was available and is available for use on future reuse projects. Of those narrowed down projects, we only have a few left, and what we're looking forward to is tying this available material that we've saved with these proposed projects, and we'll see if we can realize some of this work in the coming years. So thank you to the Park Olympique and GCPC for their enthusiasm and cooperation so far in using the roof. Thank you to all the designers in the many different stages who participated in creatively bringing ideas on how to reuse this material. So I hope to keep you updated on that in the future. Okay, let me stop sharing, and then we can get ready for our second speaker. So let me introduce Tim.
Very good.
Tim Lewis is part of the design, engineering, sustainability team at Amazon Web Services and responsible for maintaining sustainable design standards and carbon reduction requirements for AWS data centers. Tim works across the entire project timeline to execute carbon reductions with designers, manufacturers, suppliers, and contractors alike. And this involves both near-term execution and long-term strategy. As AWS aims to pilot the most innovative materials and help suppliers scale up the most ambitious decarbonization technologies. So before joining AWS, Tim spent 6.5 years at MKA, completing structural designs and carbon assessments for a wide variety of project types. Thank you, Tim. Looking forward to this.
Very good. Thanks, Dan. Much appreciated. Just want to check you can see my screen.
It's great.
Okay, sweet. Wonderful. Okay, as mentioned, we're here to talk about sustainability and the realities of construction. So as Dan mentioned, I'm at AWS, and I'm going to give some perspective about the work we do to try to put low carbon materials inside our building portfolio. So AWS, or Amazon Web Services, is a cloud computing platform offered by Amazon. We build data centers around the world, and that comes with a lot of physical infrastructure. And being that we are part of Amazon, we are also part of the Climate Pledge. So this is a commitment to be net zero by 2040. That includes scope 1, 2, and 3 emissions. And we're focused on eliminating those emissions, not just offsetting them. So there's a lot of commitments inside of the Climate Pledge, but generally it's net zero by 2040 and doing our best on the way there. So the next part is looking at what does that actually mean for our buildings. So thinking about the realities of construction and what the challenges are for our specific building types, this is a data center. Imagine you've seen similar projects, or even if these, basically these challenges are not probably unique to data centers. I'm sure you've been on similar ones where the schedule is of utmost importance. So the speed of the construction, there's immense pressure to do these projects quickly, as I'm sure lots of your projects also experience. AWS focuses a lot on consistency. It's important to our portfolio that each of the projects is the same. They function similarly across the regions. We have our carbon goals. We have targets for each material that go into the building, and those are focused mostly in the hot spots, but we're trying, to focus our attention on where we can have the most impact. And then lastly, we're kind of working on the supply chains, and we're engaging the markets before we build to make sure that those goals can actually be achieved. So I'll talk a little bit more in detail about that. So here's kind of an image of the type of building we're talking about and the structures we're thinking about. And I like to say it's nothing fancy. These are Toyota Camrys, not Ferraris. These are slab on grade, tilt up panels, steel frame, slab on metal deck. Things that we should have pretty good solutions for how to decarbonize. The challenge is they have to go fast. So we have to take the gains where we can. We think about what are approachable ways to do that. We also have in our specifications, we have a project-wide carbon reduction goal. So that means that across all the concrete poured on this project, for example, it has to achieve 35% reduction against the NRMCA baseline. So how do you achieve that? Well, we sort of presume that we're going to be able to do well in some areas and not as well in others, because we've given ourselves these schedule constraints, and we know that they're very real realities when we go to build these buildings. So to give you an example of what that looks like, here's some numbers of how we might measure that weighted average across the project. So on the left, we've got a few different structural elements. These are the types of elements you might recognize for a building that looks like this, along with the respective volumes of each. Then we measure against the NRMCA baseline. So each mix and its respective strength is matched to what the baseline would be in NRMCA. We're going to measure against that. Then we have the EPDs for each of those mixes. And then we do a volume weighted average, which on this project, the goal was for that to achieve 20. So this achieved slightly less than that. But this is the kind of math that we're doing to try to create flexibility for the contractor on how they might achieve this overall reduction. And it's worth noting in this case, you can see the tilt panels did not perform so well against their baseline, and that's due to that schedule constraint. There's extra clinker in those mixes trying to realize that high early strength. And so it's important for these carbon goals to acknowledge that not every mix is going to achieve, the greatest heights if we impose some restrictions on ourselves, namely schedule in this case. This is the same data presented a different way. So on the left, we have the baseline, and on the right, we have what the project achieved. And you can kind of see just an illustration of how this is kind of what we're trying to measure, where you can achieve in the orange here, the shear walls did okay because they were high strength anyway, so they're measured against the high strength baseline. But there's others, where we didn't do as well. So when we look ahead to how we're going to actually achieve those, we need to be realistic about how we're going to find these technologies. So we basically went and did a lot of research. So we've probably also heard a lot of these technologies, and we know that today we're using a lot of type 1L cement, which is the limestone cement. We've got a lot of slag and fly ash in the market, and we're trying to move towards the future solutions like calcined clays, different types of pozzolans, both raw or processed, different kiln modifications or clinker chemistry, as well as some of the carbon storing additives that were talked about earlier in the day today. So from the owner side, we're specifically trying to enable certain carbon reduction technologies over others, knowing that others will scale differently. So then we go out into the market. Can we find it? We basically go poking around in the places that we know we're going to build. We need to give ourselves time to go look for those suppliers, share our performance criteria, those carbon goals that we talked about at the beginning. Here's the size and shape of the building we're talking about. Can you share some, in this case, concrete mixes supplier that could help us? Once we found those suppliers who have something promising or an exciting technology off of our list of preferred favorites, then we take it to the fun part where we get to test it out in the sandbox. So we like to call it the sandbox because this is where it kind of gets real. And we're talking about before the project starts, working with those suppliers, working with usually an innovative supplier who has a new material that we want to try out, and we're building it at scale. In this case, drawn here is a full tilt-up panel, 3 of which were poured side by side to compare and basically test this out to prove if we should try it on a real project. We collected a lot of quantitative and qualitative feedback. So you're talking about sensors and data and tables and pages full of data, as well as qualitative feedback. Honestly, just written interviews, word of mouth from the people who are literally finishing that concrete. What did you think of it? Did it go well? In that example, I said we compared 3 different panels. In this case, you got 3 different cement types and 3 different binders used in different combination, and then widely varying carbon results. So of course we want to go towards panel 3, and we're trying to reach that higher level of carbon reduction, but we have to sort of prove to ourselves that it can work, because when you look at the mix designs, they're going to behave differently. There's different amounts of binder, and the binders behave differently. So we basically went through and tested all that to collect all the data. So once we have that data in hand and we know how the material works, we want to talk about bringing it onto the project, and we're basically pulling it through the supply chain. So if we have a contractor who's going to build a building for us, we introduce them to this new material, and the timing is really important there. Sometimes the bid has already gone out, but ideally we're far enough ahead and we've done enough sandbox and early work to have that material included in the bid. And then, as I said, we're kind of pulling it through the supply chain. So we've already worked with the material vendor, and then we're working with a contractor who we've hired to build the project and introducing those folks and pulling it through. The GC can get on board more quickly when we have that test data to support it. And then ultimately, we're trying to make sure that the material is ready when it's time to actually install. So we don't want to be scrambling days before a pour, thinking about what is going to end up in the truck. We should have everybody agreed, submittals approved, data to show, anticipated carbon reductions, and those are ready to go. So from the owner side, that's on us to really kind of coordinate and make sure that all of our materials are in place, and make sure that everybody understands the direction we want to go. And then lastly, we always want to have a backup option in case something's not quite as planned. Then you move into the tracking, where we want to report the as-built quantities and carbon intensities. We basically do a forecast versus an actual, where we basically take an estimate. Here's what I think I'm going to pour. Here's what I think I'm going to install. Give ourselves a chance to intervene if we need to, and then measure the as-built. How do we do when we actually installed it? So this kind of lists out that process in order. We basically went from setting the goals, looking at the constraints of the project, which are often imposed by us, the owner. We research which technologies we want to install in that building, go find out who has them, test it out in the sandbox, pull that material through the supply chain on a specific building, and then install and tally up the results. So what that might look like on your project, how do engineers kind of fit into that? We're always basically looking at what kind of detail evaluation can we simplify or modify. Always looking for reduction or replacement opportunities. Changing the standards. Can a project-specific win become standard for all the projects at your firm? Can you change your specifications and typical details to reflect things that you've learned in innovative projects? We also rely on our SEORs to work with the material suppliers and help us assess those things. We have engineering resources in-house, but it's really helpful knowing that you'll eventually be the ones looking at the submittal and offering your approval. And the last kind of goes along with that, taking ownership of the specifications and making sure our innovative materials are allowed. And then we also lean on our engineers to kind of help find those workable solutions. You lean on your experience and the decades and decades of engineering know-how that surely you bring to all of your projects as a collective body that we want to tap into and make sure we're using the best materials. So with that, I think I'll skip ahead and close out to turn it over to Max.
Thank you, Tim. And let me introduce Max before he gets his slides prepped. Tim, Max Driscoll is a seasoned practitioner of sustainability with 24 years of experience. He's currently the Vice President of Sustainability for AECOM Construction Management, where he leads decarbonization efforts for AECOM Tishman, AECOM Hunt, and leading builders group. Projects include JP Morgan Chase HQ, the Superstore in Manhattan, the Intuit Dome in Los Angeles, Tennessee Titans Stadium on Madison Avenue, JFK Terminal 1 and Terminal 6. He came to AECOM from HOK, where he was a sustainable design leader for the Northeast. There he led both project engagements and internal initiatives, highlighted by a 1.8 million square foot net zero corporate campus, the LaGuardia Airport Terminal B, and firm-wide interiors sustainability strategies. Thank you, Max. Looking forward to what you've got here.
Cool. Thanks, Dan. Are you seeing the presentation mode or the slide sorter mode?
Presentation mode.
All right. That's always a crapshoot for me. So as Dan said, I'm the sustainability lead for AECOM's construction management group. That's for most people in New York City and around New York City know that construction or that construction manager as Tishman. So that's AECOM Tishman. And through the rest of the country, probably more well known as AECOM Hunt. Tishman tends to build skyscrapers, like I said, in and around New York City, and Hunt tends to do what I call low and long buildings, arenas, stadiums, and airports. So I'm going to be talking about embodied carbon in the construction manager or the contractor's perspective. And how we're trying to pull the market along and lead in that. I'll go through this quickly. It's probably speaking to the choir here, but just to point out that for quite a while we've been talking about operational carbon, energy consumption in buildings, but not much about embodied carbon. And this graph just kind of highlights the fact that in terms of global CO2 emissions, a large chunk of that emissions profile sits in the production of mostly construction materials. And so if we don't address construction materials, we are not going to get to our climate targets. And so how I've started to reframe that among clients or design teams is this idea around a total carbon picture. So it's not just operational carbon, but it's both of them together. So operational plus embodied. And this graph just kind of highlights the fact that, with embodied carbon at the bottom in blue and operational carbon on top in green. So say in year 0, you're already sort of in the hole, so to speak, in terms of the carbon footprint of the building. And then as the operations proceed, you're stacking up operational carbon, but we're talking about all electric buildings and a greening of the electrical grid. So that potentially, theoretically, can go to 0. But what you're left with is what I call a non-dischargeable carbon debt. Anybody that has had student loan debt can sympathize. unless you attack that that debt early in the project, in year 0 or prior to that, in pre-con really, you're going to be left with that carbon load on that project. So that project can never truly be a net zero a building when looking at it through the total carbon picture lens. So where we are as a company, and actually we're also a part of the climate pledge that Tim mentioned earlier, but we do have a corporate strategy, and net zero is one of the pillars there. We have a 2040 target to be net zero as a total corporation. So that includes the construction management group and the design side of the house. But the reality is, oh my God, all of our carbon sits inside of our construction group. So this was a realization, I think, that happened a couple of years ago that led to the creation of my role. So my role is brand new within the business, about 2.5 years old now. And really getting our heads around our emissions profile. So in teal, you could see that's our scope 3 profile. So 97% of AECOM's carbon footprint is scope 3. So it's basically all scope 3. And then of that scope 3, when you break it down further, 80% sits inside of construction management. So really for AECOM corporate to succeed, we have to succeed on the construction business. And frankly, we haven't ever really done it before. We've been talking about operational carbon for 40 years. If you look at the evolution of the energy code, how many codes have embodied carbon requirements in them? Very few. I mean, it's starting to grow, but it's a very, very new area. This is something we just published. So feel free to go to the website. You can either go to the Tishman or the Hunt website, click on sustainability, and you'll see a link for this document. In the spirit of leadership, we are trying to, pull the market along. And so we disclosed our decarbonization strategy as a construction business, but also for those of you that have to do carbon disclosures, we went through our whole materiality analysis in terms of scope 3, which categories we picked, which we didn't, the rationale for both of those selections. And also there's a third selection in there, which ones we're sort of monitoring in the case where there may not be data available or we think it might become material in the future. So it's not long. We try to make things pretty short and to the point. I think it's only 4 pages, but it describes, again, our process, and also the scope 3 materiality. So if you're starting your journey or are interested, this can be a helpful document to take a look at. So we get into the meat of it here. So what are we actually doing about it, right? We have this big problem. Some folks are saying, well, we're constructors, we're just building what's designed. We take the spec, we take the drawings, and we just do that. So that's kind of the old school mentality. What I'm trying to change and bring to our business is actually, that's not the case. We do have a lot of influence. We hold the paper, as we say. So, for our supply chain, for our subcontractors, we're paying them, we're selecting them and paying them. So we can exert some influence into the supply chain. And so this is the strategy that I've been implementing over the last 2 years. And really we'll focus today on the projects. So it's number 1, measuring carbon on our projects, as Tim alluded to earlier, getting EPDs, getting quantities, and starting to make those measurements. Oftentimes what's disclosed in the Fortune 500 in those carbon disclosures that you'll see in the public reports are based on spend and emissions factors. And so what we found is that when we actually measure carbon with EPDs on projects, those numbers actually come down. So we're seeing a benefit in getting more granular with the data, even though it's harder to do, but it's worth it. And so what are we measuring? Oh, not a shocker to anybody on the call, we're measuring concrete and steel. And then this year we've actually rolled facades into that grouping. But and so this is how my approach to the company has been to take this giant problem. Oh my God, net zero by 2040. The construction business hasn't changed dramatically in the last 100 years. So how do we sort of turn the ship around into sort of, and by doing that, I'm saying we got to kind of narrow it down like a funnel into more digestible, more bite-sized pieces. And so what I talk about internally is, fear not, we only have to tackle 2 trades, right? It's not, we don't have to tackle all the million parts and pieces that you would use to build a project. If we tackle concrete and steel and facades next, we're a long ways away toward a sort of a runway or a pathway toward decarbonizing our business. And so this is a workflow that I've developed that we're implementing on many of our projects, some of the bigger ones especially. And this might be useful for this audience. Oftentimes when I start this process, we get a pre-con assignment, a pre-construction assignment. The carbon kickoff obviously involves the structural engineers and other design team members and the client and the owner's rep, but the structural engineers are really the key player in that. And so I've been met with some surprise on the structural engineering side to say, hey, you're interested in carbon? And I say, yeah, we're interested in carbon, and let's work together to figure this out, set some targets. And then we kind of go through a process where we're working collaboratively. I think you probably heard that a lot today. Collaboration is how you succeed. But we're going through this process, and highlighted in green there is that key phase, the subcontractor engagement that we do, right? So the structural engineer may have an understanding, a broad understanding of the market and what the market can deliver, but they don't have that real-time information in terms of cost, availability. Is a subcontractor comfortable pouring low carbon concrete? So that's where we come in, and when we do that really matters, right? So we do that pre-buyout when we have leverage, and that's like the most important thing in this whole diagram. Is we go and engage the market, especially on a big job, and mainly with concrete more than steel, but we'll go engage the concrete subcontractors and then their potential ready mix suppliers in that market and say, hey, what do you think about these targets? Is there anything new that you're doing that you could bring to the table? And so we start that conversation pre-buyout when we have leverage, because on the big jobs, they often want to win those jobs. And that's when you can kind of manage that cost premium downward, if not eliminate it altogether. So some success stories. These are 2 different projects. Can't divulge names and addresses, but one is the large stadium project where we executed that carbon workflow. And as I sort of just alluded to, we got 3 of the largest concrete ready mix suppliers in the area that we knew could service the job. We got them to present to us, so us being the construction manager, the structural engineer, I think the sustainability consultant was involved, and the owner's rep. We got them to present to us their sustainability approach for concrete, which was the first time I've ever done that, but it was great. And toward the end of those presentations, I had to ask them point blank, what's the cost premium for low carbon concrete? And all 3 of those suppliers said there isn't any, which kind of surprised me, but also didn't, given when we were asking them that question. So for that project, we were able to deliver a low carbon project. The overall target was set at 20, as Tim alluded to earlier. It's not a prescriptive GWP reduction requirement. We allowed flexibility within the individual design mixes should you need to have a high strength mix or a high early strength mix, or weather conditions made it so that you couldn't use the SEMs that you were planning on using. So there was flexibility in that, as long as the overall weighted average is hitting that mark. So the other nice thing about this project is we got buy-in on a little market transformation pilot using ground glass pozzolan, which they had never used in that market before. So because we asked the questions early, because we put it in the bid scope and it wasn't a change order, a lot of these things are able to happen. So it's, in a way, it's what I've realized, it's not about technology, it's really about process. So we could take big bites at the apple with what's sort of in the market right now. Fly ash slag, GGP is relatively new, but becoming more and more commonplace. Another sports project. This is just an example of the result of that early engagement with the structural engineer. So, we were talking to them about writing some specific SEM replacements for concrete into their spec, and they didn't like that. They didn't want to change the spec. So what they did is they put it on the general notes sheet. So we got this level of specificity on the general notes, which was I think really important. So when we were then taking these drawings and specs to the subcontractor market, it was crystal clear what the expectation was. So this is like a fine detail, but I think really important, right? Don't just put minimum, or no, in the specs I'm seeing a lot of maximums, but no minimums for say fly ash or slag. So I've our subcontractors have interpreted that as, well, I could go with 0% and still be compliant with the spec. And so that's kind of not where you want to end up. This is a different project where we have some data and we measured for concrete and steel. The overall reduction sounds low, but it was a giant project, 2.5 million square foot skyscraper. So 10% reduction, but that equated to 14,000 tons of CO2 avoided. And that sort of doesn't mean much to a lot of people. So I use these equivalencies, 36 million miles traveled, or 1,400 times around the earth. You can have fun with those, millions of acres of trees planted. But really it was about getting ahead of it, getting the structural engineer on board, and measuring it. And, it sounds simple, but oftentimes some of that stuff slips through the cracks. And then on the same project, two little deeper dives here. Interesting kind of convergence on high strength concrete and carbon reduction. So, the higher the strength required. So we'll, on these big skyscrapers, we'll use 10, 14, 16,000 PSI mixes for foundations. And they actually perform better with more SCMs, or more fly ash or slag. So there's a nice convergence of carbon performance and structural performance there. So, keep that in mind if you're speccing. If you could maybe go from a 6 or an 8 to a 10, but that means you can get more SCM in the mix. There's a sort of balance to be played there, which is kind of an interesting thing to kind of think through. And then the other bit that I talked about is ground glass pozzolan. So this was the largest deployment of that, 2.5 million square feet of floor slabs. It was slab on metal decks, so relatively low PSI, 4,000 and 5,000, and the carbon reductions weren't as good, sort of on a line item basis compared to the high strength foundations, but it was like a market transformation strategy where we're allowing that smaller ground glass pozzolan facility to scale because of the scale of the project. The nice thing here is that it also has a circularity component, provides a market for conventional glass recycling, glass bottle recycling, or they'll even do facade deconstruction, so glazing. That's another interesting thing we're exploring in terms of circularity and waste, but a topic for another day. Yeah, that's all I've got for you, and I think we'll open it up for questions.
Thanks, Max, and thanks, Tim. That was really great.